Yeah.
Okay. How are you?
Yeah, I'm fine. No, teaching has not started yet. So
Yeah. So tell me one thing. So would you like a 45 minutes break, or you want to make it at a stretch for 1 hour, 15 minutes, 20 minutes, and then 10 minutes question?
Maybe we'll break. That will be convenient. Yeah.
Okay. So you just tell us when you want to take a break.
Yeah. Right.
We can go depart for a water and tea for 5-10 minutes, and then we can come back.
Yeah. Right.
Okay. So let us start then.
Sure.
Good morning to everyone. So from today we are starting special lectures on surveys in differential geometry, and in this series of lectures, almost all the eminent professors of differential geometry of the country are lined up for their special talks throughout this week, and it is my pleasure and honor to host all these eminent personalities in this NASI TMC summer school on differential geometry. And in this series of lectures, today we are starting with the lecture of Professor S.G. Dani from JFR, Mumbai, who is Santi Sarup Bhatnagar Awardee. So for the start of proceeding, I invite Dr. Krishnendu Gangopadhyay, co-convener of this workshop and head of the Department of Mathematical Sciences from ISER Mohali, to share this session. Over to you, sir.
Okay, so welcome everyone to this workshop. So as you know, this workshop connects the 2 weeks course on curves and surfaces that you have seen, but it will be more. It will be a survey of more advanced topics that will give you some idea of some of the research directions that we can pursue. Now, it is a great pleasure for me to have Professor Dani for the talk today. So, Professor S.G. Dani, who is very well known in the field of Lie groups and dynamics. So, he is currently a professor of mathematics at the IIT Bombay.
no.
But before joining IIT Bombay, he was a professor at the Tata Institute of Fundamental Research for more than 30 years, and he visited many premier institutes around the world, like Institute for Advanced Studies and other universities of eminence. And Professor Dani was the chairperson of the NBHM from 1996 for around 10 years, and he won the Santi Sarup Bhatnagar Award in 1990, gave an invited talk at the ICM in 1994, and he has also received the World Academy of Science Prize, the third World Academy of Science Prize by the ICM. So it is indeed a pleasure to have Professor Dani here. So sir, I welcome you to start your talk.
Hello. Good afternoon, everyone, and welcome to you all to this talk. So, I'm going to. You have had some exposure to various topics by now, and this I think we are in the third week. So I do hope I'm going to talk. I mean, I suppose the topic has been announced. It is some hyperbolic geometry, with some special emphasis on the modular group and continued fraction expansions, and their interrelations is what we'll be talking about. So I'll share my presentation.
Yeah. So please share your presentation. Yeah, no problem. I hope there is no problem here.
Can you see the presentation now? Okay.
Yes, sir, it is fine.
Yes, we can see that.
Right. Now, before I begin, let me make a update. Tell you an update on what Krishnendu mentioned. After completing my after TIFR and also completing 5 years at IIT, as you mentioned, I am currently at this UMDA Center for Excellence in Basic Sciences. This is an undergraduate institution like ISER and itself.
Oh yes. Sorry, I missed that. Yeah, absolutely.
That's fine. That's fine. Yeah, and it is run jointly by the University of Mumbai and the Department of Atomic Energy. So we have a similar system like ISER with a nationwide selection process, etc., which is coordinated with NICER Bhubaneswar. Anyway, so let me come back to the topic, and before that let me at the outset thank Professor Krishnendu Gangopadhyay and the organizers for this opportunity to me to give an exposition on this topic to you. Okay, let's begin with hyperbolic geometry. Some of you may have some familiarity, but maybe I'll sort of try to be a little more comprehensive than simply saying that this is the hyperbolic plane, etc. So I do hope even for those who have some familiarity, what I'm going to say would help. So the aim of this talk is to give an exposition, as I said, in the connection between geometry and of the Poincare plane with continued fraction expansions of real numbers, and what is involved in this is very certain Diophantine properties of real numbers. Now we will know more about it as we go along. We begin by recalling some basic facts about the upper half plane, which is equipped with the Poincare metric, which I'm going to tell you what the Poincare metric is. It's group of isometries, then the modular subgroup, and then I'll introduce the geodesic flow firstly of the hyperbolic plane itself, and secondly of the modular surface, then associated with the quotient modular surface. The modular surface itself will be introduced as a quotient of the hyperbolic plane. So some of the many of you perhaps this is going to be new, but I'm going to say more about this. This is just a sketch of what we're going to talk about. Okay, so in the second half of the talk, I'll talk about continued fraction expansions. I'll recall what they are, as some of you may not be familiar with what that means, and of real numbers, and discuss the interaction between geometry and arithmetic through considerations of the modular group and the geodesic flow. Okay, let's begin. So the Poincare plane is, though it's called a plane, which should do it is like a plane, but you have to understand it more intrinsically and more abstractly. So let H be this subset of the complex plane consisting of the upper half part. So I'm taking all Z complex numbers x plus iy with y positive, strictly positive. So I'll have some diagrams, but for the moment you can surely use your imagination to see what this means. So okay, now, and this is equipped. So on this is our space, a manifold. It's a surface. You already have exposure to geometry, so you know that you can recognize this as a surface, at least topologically. And now we equip this with the Riemannian metric given by dx square plus dy square divided by y square. So at each point, of course, of the complex plane, we know this numerator as a Riemannian metric. That's the usual Riemannian metric, but we are going to modify it. At each point, it's going to be modified by dividing by the quotient y square. So this is going to be the distance element, as we call ds. The distance between two infinitesimally close points is going to be the square root of this expression here. I'll say a little more about what this means. Okay, this means that if you take a piecewise smooth curve, say parameterized from 0, 1 to into h, and you write it. This is going to the complex plane, so I can write this gamma t as xt plus I times yt for all t in 0, 1, and the length of this curve under this metric will be given by you take the derivatives dx by dt square the dy by dt whole square. Now this is the normal distance element. So for the length of gamma in the complex plane itself, you would have simply integrated that. But now we are modifying it by the factor 1 over yt. Remember that we are in the positive part, so this number is necessarily positive. It is not 0, it's not negative, it's always positive. So this is going to give you, of course, the square root, I mean to be the positive square root. So this is a positive valued function being integrated, non-negative, I mean, okay, it's so. And then this gives a certain number which is considered the length of that curve. Now, when you since you know, I mean, in Riemann geometry, you can think of the distance between any 2 points of the manifold. In this case, our surface H here, as given here, is the infimum of. You take lengths of all curves joining the 2 points. Given any 2 points, you should take consider all possible piecewise smooth curves. For each of those, you have the associated length, and then take the minimum, take the infimum of that, and that is the distance between the 2 points. Now, of course, notice that the distance in the complex plane and the distance in the hyperbolic plane are going to be different, not just in numbers, but also quite very qualitatively, because so, of course, if you stay in the region where this y is bounded away from 0, then maybe you can simply scale things up and down so that there's not too much distortion. However, if when you are looking at regions which are where yt is very small, then this distortion can be very large. So I'll say more about this when you go to some picture diagrams. So for the moment, this is the notion of lengths and distance that we are concerned about. Now, with a Riemannian manifold, like for a general manifold, you say if it's a smooth manifold, the diffeomorphisms tell you about that manifold. For a topological manifold, you have the class group of homeomorphisms tells you more about the what the manifold has specializes in, etc. So now, when you're in the Riemann manifold, when we would like to look at the isometries, what are the isometries? What are the points? What are the bijective maps of the manifold surface into itself, which will leave the metric invariant, or the distances invariant. The two are equivalent. The metric will remain invariant if and only if the distances are preserved. Now, there is one way of arriving at this group, which I'll jump to directly. And for that, let me introduce the following. Let SL2R, this is a familiar object to everyone. So with a group of 2 cross 2 matrices with determinant 1, and I'm going to do a bit of tweaking with the group. What I'm going to think of is a new group where SL2R modulo plus or minus identity. Now, plus or minus identity, as you see, is a normal subgroup of this. and it's a closed normal subgroup. So I can take the quotient of this. So in other words, I am not going to distinguish, though I'm going to think of 2 cross 2 matrices with determinant 1, which is multiplicative group with the usual multiplication, etc. I'm not going to think of that group itself, but whenever I have 2 matrices with this and one differs, entries of one are simply the negatives of entries of the other, I'm going to think of them as being the same. This is what it stands for. So in other words, the 2 matrices which differ by multiplication by minus identity will again be treated as same. Okay, so why am I interested in this group? It is the following. Now, first of all, look at the natural action of SL2R on H. We have a natural action of H, which you would have seen in various contexts. It's called the fractional transformations or a variety of names, but the action is the element point Z is taken to AZ plus B upon CZ plus D for all Z in H. Now, you can verify that when I have Z, this Z is in the upper half plane, and the matrix ABCD is from SL to R. This num is defined as a, first of all, this CZ plus D will turn out to be non-zero, and this actually defines a proper complex number. That verification I'll leave to you. So, and now it is straightforward to verify that each. This defines a group action. It's straightforward to verify that for every choice of the matrix ABCD with forming a matrix in SL2R, this is actually an isometry. I'll not go into the full indication of that, but let's say take simple matrices like say A equal to 1 and AD equal to 1, C equal to 0. Let's say take upper triangular matrices. Then notice that this transformation is simply Z going to Z plus B. Okay, and notice that your Riemannian metric is invariant under. This will remain unchanged when under the transformation X going to X plus B. Because on both sides, when you divide by y, you are dividing by the same y, so the distortion is precisely matched. Similarly, you can if you take diagonal matrices, you can see that it is this is multiplied by. So diagonal matrix of BC are 0 and D is A inverse, then this is the transformation is simply Z going to A square Z, where A is a real number. Now in this case there is actual distortion, but it happens in such a way that it actually matches. Anyway, so one can verify by fairly straightforward computations that no matter what matrix you are taking, this transformation is actually an isometry. So now we have the SL2R action, but the thing to note is that if I take the element minus identity, it acts trivially. It takes Z into itself. So A and D are -1 and B and C are 0. So this is the identity transformation. So this subgroup is acting trivially. It's not changing any point of the space at all under its action. So therefore it means that actually I can think of this action as the action of this group, quotient group, which is the group of isometries. So, and therefore G there, and none of none of the other elements. So if I take any element other than plus or minus identity, then you can see that it's easy to see by simple manipulations that there will be points which are not fixed. So therefore, every other transformation that you see here is a non-trivial isometry. So you can think of this group G as a group of isometries of G. Now, not only that, this actually covers a pretty large, large class of isometries of the group. In fact, any isometry which is orientation preserving, I'll not go into the details of these terms, so that you can think of, many of you would probably know, and even if you are not introduced to it, you can usually intuitively understand what this means. So, for instance, if you what is a matrix which does not belong here? So, for instance, you take 1, 0, 0, minus 1. Okay, so and that acts as that will act by flipping. So and so you can it's going to take x y into on the other side of the imaginary axis. So this will change the orientation of the plane. And that's an isometry, but it doesn't preserve the orientation. And one can show that any isometry which preserves orientation is actually given by an element of this group. So this is actually the group of all orientation preserving isometries of Z. So this is a brief recollection about what the isometries of H, introduction to that. Let's recall about geodesics. So what is a geodesic? On a Riemannian manifold, it's a curve is called a geodesic if it is locally length minimizing. So what does it mean? So you can think of curves which are which minimize the length of. So if you have 2 points, you can think of curves for which the length is the minimum possible. The distance you know is the minimum of infimum of all lengths. Now, in good cases, you can expect to have a particular single curve where the minimum infimum is attained, and that's the minimum. And such a curve is like in the plane, the straight lines are the geodesics, right? So these curves generalize to Riemannian manifolds as geodesics. But we don't always demand that the length is minimum all along. For a curve, you don't ask for the curve to be length minimizing as such, but you expect only that if you take little segments of that, they are length minimizing. You realize the importance of this locally. Why you should do it only locally? If you think of, say, for instance, the sphere. So this is, of course, this is going to be a bit of a digression. Now, on a sphere, if you look at the great circles. So if you take nearby points, then the great circle is the curve along which the length is minimizing. Right? But if you take, if you're not taking the full great circle, but leaving out, say, an arc, you should still think of that as the geodesic between the curves, but it is not length minimizing because if you have taken out some part, so it's only minimizing only one of the two arcs that are formed, that will be length minimizing, while the other part should also be thought of as the geodesic. So this lacuna is taken care of if you assume not that the curve should be length minimizing, but only locally, if it should be possible to cover it by segments where the curve is length minimizing. Anyway, so I'm sure all of you have some exposure to all of this, so I need not repeat all this. But I thought, my own contribution to clarifying some of this might help you. Okay, so now let me also recall a few things that you might already know or can believe at this point, and will not go too much into the details. In a Riemannian manifold, given a point P and a direction from P, so I should actually assume completeness or something like that. Let's say we are taking good manifolds, and our hyperbolic plane is one such. So given a point P and a direction P, there exists a unique geodesic passing through the given direction and is tangent to it. So given, if I take a point and have a direction, then there is even without completeness in any Riemannian manifold, there is a little geodesic segment that you can draw around it, semi of size epsilon, some epsilon, which will be a geodesic segment locally. This is something of a very standard fact in Riemann geometry. Okay, so now let's think of what are the geodesics here in H. It's immediate to see from the formula that the vertical lines, which we shall write as gamma s equal to s plus I times e power t, where s is in R, these are geodesics. Why is that? Because now if you have a curve, and if you take the corresponding curve, if you ignore the y coordinates and take the corresponding curve along that particular vertical line, then that is going to have length by this formula, which is less than or equal to any other. So let's think of this line as the imaginary axis. And on the vertical, if you have 2 points on this vertical, and I have some curve which leaves for part of the time is outside, and then at the end comes here, it is necessarily going to have greater length than the corresponding curve that you would get simply by projecting to it. So it's clear that the vertical lines are length minimizing, and so of course with the length would depend on the parameterization also, and you can see that this parameterization, which doesn't involve going back and forth. I mean, one can check that for this parameterization, this will actually be minimum. So this is the vertical line over the point x equal to the x coordinate being s, and so these will be geodesics. So without having to solve any differential equations, etc., you can confirm that this is actually a geodesic. Now, secondly, we see that if I take any isometry and apply it to gamma s, that must also be a geodesic, right? When we apply under the application of isometries, the local length minimizing property is not going to change. Therefore, all these are also isometries, right? Now, okay, so we have got hold of a whole lot of isometries, and here, and then okay, since this I already said. It can be seen that every semicircle. Now, first of all, if you take any vertical line and apply, you remember that this group of transformations that we are involved with has the property that every family of circles and straight lines together is invariant. So every circle goes to either a circle, straight line, or a circle, or as well as every straight line goes to a circle or a straight line itself. Right. So the vertical lines under the transformations are going to be circles, and they're going to be, you can check moreover that they're going to be their part in the upper half plane is actually going to be a semicircle. Semicircle with endpoints in R. So our upper half plane has the real line at its base. So that you can think for the curves which are sort of trying to leave the upper half plane, there can be there are you can think of the endpoints, limit points in R, and so the G of gamma s, each of these G of gamma s is going to be a semicircle which joins the 2 points, namely G of 0. Let's say you are taking image of this under a G, then this goes from, sorry, there is a typo here. This should be T greater than 0. No, this is okay. No, T goes here. I have written e power minus T here, e power T here. So as T goes is in R, so this segment of the vertical line has imaginary parts going from 0 to infinity, and that line will be under the action of G will be a curve joining G of 0. G of the point G of S and the G of infinity. So G of S. So the two, and if you think of the semicircle joining G of S and G of infinity, these 2 points, that will be the image of gamma S. I wish I had some of the figures I should have brought here also, but anyway, should be clear. Now this is a rich collection of curves that we have found, which are geodesics, and it turns out that these are in fact all the geodesics that you can have, because first of all you can see that given any point and a direction at that, there will be one of these which passes through that point and has the given vector as the tangent. So it shows that this set of class of curves is actually adequate. Now, given any point, okay, this is what I mentioned already. Given any point P and there is a member of the family that we have, a circle. And okay, here is at least one picture of the geodesics. So let me recall some of what I said earlier in terms of this picture. We have the upper half plane here. Now these semicircles, they are now geodesics passing through now this point itself, the point 0. Or what is marked as B infinity here, this is not a part of they have upper half plane, but it is you can think of this boundary and its limit. It has this as one boundary point, and there is another boundary point. So this semicircle is now a geodesic in the upper half plane. Similarly, for every semicircle here, it's a geodesic in the upper half plane. And notice that what is the family of circles drawn here, they have a certain common limit point, because geodesics do not meet each other in the manifold, but at the boundary they are going to have the same limit point. So what it means, and in fact these distances between them, they are they are going to zero not only in the usual distance, but in the hyperbolic distance also. You can have a matching of the points so that they are going to zero. Yeah. So if you think of, for instance, if you take two vertical lines, then the points at the corresponding heights are, though in the Euclidean distance is fixed, the hyperbolic distance will be going to zero as the height tends to infinity. So there is a difference between the Euclidean and hyperbolic geometry that is seen here. So this is what is drawn here is in fact a class of asymptotic geodesics in the upper half plane. Okay, now let me go to the next object that I need you to be familiar with. So now SL2R, well, this group was already introduced, and G is equal to this. Now this is called. No, SL2Z is now the subgroup consisting of elements of SL2R which have integer entries. Okay, so now this we are looking modulo the plus or minus identity, and similarly we shall look at this also modulo plus or minus identity, and that is called the modular group. So it's a discrete subgroup of of the group of isometries. So gamma is a discrete subgroup, and it acts properly discontinuously. I'll not go into spend time on the definition of this, but this means that points which a convergent sequence comes only from a convergent sequence. That is what it means. But this is not. But it can have fixed points. So if you have something which is properly discontinuous and without fixed points, then the whole picture becomes sort of like from the Euclidean space to a torus. So there is a covering map. But this is not the quotient here is not going to be a covering map because there are fixed points involved. Now we form the quotient space H modulo gamma. What does it mean? It means that you take when you have 2 points of the hyperbolic plane, you're going to identify that into a single point as being the same object, same point of our new quotient space. If the two of them, if one of them can be moved to another by an element of gamma, and this is of course a symmetric relation. It's an equivalence relation. So the modular surface is the equivalence set of equivalence classes under this equivalence relation. Now, rather than this whole on the upper half plane, the gamma is an infinite group. Infinitely many points are going to be identified with each other, which would be somewhat difficult to imagine, perhaps in some way, unless we are used to it already. But there is a simpler way to do that. Let us look at this particular subset. So f equal to x plus iy, where absolute value of x is less than or equal to half, and the absolute value of z is greater than 1, greater than or equal to 1. This is a fundamental domain for the action of gamma. Or what does it mean? It means that every orbit has at least one representative in F, and those points in which are in the interior of this set as a subset of the plane, then they have unique representatives. So let me now go to my next picture. Okay, so my subset F, you can see, is drawn here in gray. There's some scale which you can ignore. It doesn't matter. This is the unit circle. These are lines, real part equal to half and minus half, and real part equal to half. So the region is between these two parallel lines, real part equal to minus half and real part equal to plus half, but outside the unit disk. So it's like a triangle, except that these are geodesic triangle. The boundaries are geodesic. This is a geodesic, as well as these two are parts of geodesic here. So it's this is a geodesic triangle, which describes a certain set as its interior, and this is a fundamental group in the sense that every point turns out to have a representative here. Now, for the points on at this level, you can see it's easy to see that if I take the point that I am where I have my such lens here, so I can translate it by an integer. So recall that z going to z plus 1 corresponds to the action of the unipotent to the triangular matrix that I talked about. So I can move it by a single iterate of that. I can move it here, then I can move it here. So in this point, the corresponding region here, if I apply to this part the transformation z going to z minus 2, which actually corresponds to the action of 1 minus 2 0 1 as a matrix. So then the whole thing will come here.
Yeah. So Professor Dani, excuse me. So there is a question probably. So Amita Sharma, what do you want to ask?
Okay.
Amita Sharma, you have raised your hand. So is there any question? Hello?
Yeah.
Okay, so I think there is no question. You can.
Okay.
Yeah.
So coming back to what I was saying, every point has every point in the upper half plane has a representative in this part, and if the representative, when you think of points inside that, the representative is unique. Now, by I'm suggesting that for the boundary points, the representative will not be unique. And so, what are the what are the points which can be related to each other? It's good to know. So, if you look at a point on this line, then I can always translate it, and it comes to this line. So, therefore, these 2 points at the same height, they are. Though both of them are in F, they are still equivalent. So there is some further identification being made. So even within this triangle, I should be identifying this point to this point. Similarly, you will notice that if I take the transformation z going to minus 1 over z, which also comes from an element of gamma, then this flips. This triangle, geodesic triangle, will be moved to this, and in the course of that, this arc, this boundary will be reversed. So this point will go to this. This point will correspond to go to this point, whereas this point will be fixed. So these points are at corresponding points, reflected points. They are actually going to be identified, and up to this end. So. Therefore, now these are further identifications that are being made. So we should think of the quotient space as, so you have this piece. If you think of this as a piece of infinite piece of paper, let's say, with here this part cut out here. Now you should glue. We want to glue this side to this side, so that it will look like now look like a cylinder with some part cut off here. Right, and this to begin with, it will have a hole here, but that hole is not going to be left there. This it's going to be glued in such a way that this point goes to this, etc., up to here. So this whole thing is going to be patched up. Okay, and now it's a good exercise to see that when you do this is actually as topologically this is a space which is homeomorphic to R2, the plane. So I mean, this more or less is like a circle. On the other hand, its analytical properties are quite different. So which is what will concern us. Now I'm going to take a few more minutes, and then we'll have a break. See, the modular surface can be realized as the quotient. All this I have said. So they're precisely so. Now because of the structure of this, I'll just say this. Just more heuristically, you see that at each of these so these two sides are attached to each other. So at each point there is a whole 360 degrees and element coverage here. So when you group, but there are these apparently 3 points where that will not happen. So when you glue, this is some 60 degrees, I believe. So the angle here will come together with this angle, but it still adds up to only less than 360 degrees. So, and similarly here there is only 180 degrees and at this point. At all other points there you will have added 180 degrees, one side added to this side. So there are 2 points here which are singular, they're quite different, and we will be leaving them out of consideration, so I'll not say more about that. But at all other points there's a nice geometric structure, and the whole thing is a nice surface. So there are regular points with a nice surface structure. So that's the modular. So now a few things about the general structure of the modular surface is in particular you see that it is non-compact. The bottom part we have patched up, so there are no additional limits, etc. But the other part, so there are sequences here which you take. If you take the imaginary parts going to infinity, then they are not going to have any limit. So these are the space is therefore non-compact. But note that in fact non-compactness arises only from this kind of tip. It's as if it has a certain sharp point, and you can be getting out. You can be leaving the space, getting outside the space, which is possible in a non-compact space, more or less in a unique way. The only thing that can happen is that the imaginary parts of the corresponding points, they are going to infinity. Such a thing is called a cusp. So it's a surface with a cusp. Okay. So perhaps now let's take a short break and we can start on this geodesic flow on this, which is the crucial part for the second part. So we'll take a break for 5 minutes.
Yeah, so we take a break for 5 minutes and we resume at 11:50.
55.
Okay. 55 at 11:55. Yeah. Okay, so Divya Jyoti, what is your question? You have raised your hand. Divya Jyoti, is there any question? There is a hand raised. Is there any question?
Divya Jyoti, have you any question? Divya Jyoti. I think she has no question. She has accidentally raised.
Would it matter if I overshoot a little, or do they have something immediately?
Well, no, there is nothing. There is lunch after this, so if you want, you can take a few minutes.
Okay, good. So I won't, okay, I'll follow a natural pace and not rush myself.
Yeah, absolutely. No problem.
Hello, Ravi.
So, yeah, Professor Kulkarni seems there, but I do not know whether maybe he has gone for a break.
Pardon?
Professor Kulkarni, you say hi to him, but I think
Yeah. We greeted each other. Yeah.
Hi, yeah.
Sir, if possible, please increase the size of PPT, if possible.
Pardon?
Enlarge the PPT size. Enlarge.
No, that's okay. I think the participants can enlarge their screen. You just press Control plus or Control Alt plus. It will be increased in your screen. Yeah. So like I zoom in, I can see it nicely. No problem. Yeah. So if somebody cannot see the PPT properly, just enlarge your screen font. Okay. So it is most of the time it is a local problem. Okay, so in a Windows system, it is Control Alt plus. That's what you have to do. Or maybe Shift plus. Shift plus. Shift plus. Whatever. Okay, so Professor Dani, may we start? Okay, he's not there. Good. So Divya Jyoti has again raised the hand. Maybe you can ask if you have any question. So there is a hand raised. So the participant may ask if he or she wants to ask anything.
App. Raise hand. Raise hand.
We have
Participants. Participants can raise hands to ask.
Okay, it seems it's not intentional. So maybe by touch screen, the hand has been raised. So if Divya Jyoti is there, either you ask a question or lower your hand. Okay. Anyway. So,
Now,
Professor, yeah. So may we start? Yeah. So we can start. Yeah.
Can we start? Welcome back.
Yeah. Sure.
Yeah, so I introduced this modular surface, and it's the geodesic flow on this that is going to be the object of interest for us through the rest of the things. So we shall leave the singular points. We shall leave aside. Let's denote S by S the set of regular points. Let me just clarify that there are actually only two. So we are thinking of the surface where these two sides are glued point by point wise, and then these are glued in the opposite direction. I mean by symmetry. So that I said these 3 points are different, but actually in the quotient these two are actually same, whereas this is different. So there are two singular points, but which we will be leaving aside, and think of the surface and the flow on that. So the Poincare metric induces a metric on that. So we can think of distances. Let me just mention this and then go to the picture and explain that. And we shall consider the space equipped with with this distance and the corresponding Riemann metric. Now the flow that we will be talking about will be defined. It's not taking just point to point, but the initial data, object that you start with is a point together with a given unit tangent direction at that. Okay, and for given such a thing, we associate with it for any time t a transformation phi t, which is given as follows. So let gamma be the unit speed geodesic, which starts at p and is tangential to the given theta. Okay, and now define pt as equal to gamma t and theta dash t equal to theta t equal to gamma dash t. And here is what is happening in the picture. Let's take any. I've started with this point, but you might as well start at any point here. So, and let's say you are given the direction which is going in the direction of this curve. Now take that point, take the direction that gives you a certain geodesic curve in the upper half plane, right? So you follow this geodesic plane in the upper half plane, but these geodesics, they're from the upper half plane, they are not they don't stay within this set F that we have. So when it okay, let's say, yeah, I think I wanted to start here. So start here, then it'll the curve takes you all the way up to here. Now this point as far as our surface is concerned, is the same as this point. So this will flow will continue and give you a flow here. So next time you will come here, and then again this point is identified with another one, and it will from here you will go onward and so on. So I suppose you get the picture. So starting from any point, the point itself doesn't tell you which way you are going. You have to go. You have to have a point and a direction. So given this data, a point and a direction, then for any time t, you can define phi t of that, and it is. So again, let me repeat. Let's say if I start from this point and going in that direction, then I go along this. So if my time t is already before this, then I will have that point as the corresponding point. If my time t at which I want to know where it went, if it goes beyond, then I should follow the tracks here according to the identifications that we have, and I get a point. Let's say my t corresponds to, let's say, something coming here. Then I get a new point which is pt, and at this point the geodesic is headed in a particular direction, and that is the direction that you want to record. So the phi t of the pair pt is given by pt theta t, which is where pt is the point on that geodesic which is at distance t, if t is positive, and you can do the corresponding similar thing on the negative side. And the direction you are keeping track is the direction where the geodesic is headed at that time. So notice that if you do it, if you have s and t, if you repeat this, say t1 and then t2, the result is, the combined result is going to be the same as the what you do individually. Say s first. Let's say my time s is such that I go from here and then go here, and then this is my s. So at this point, I will have recorded this point here together with the direction in which it is headed. Now, when I apply my t2, so I'm starting from this point and this direction, and then going for time t2, and say coming here and then coming here, etc. So I would be doing the same. I would have achieved the same thing by starting from here and following this for time t1 plus t2. So this is actually a genuine flow with appropriate time behavior. Okay, so that is the definition of the flow, and now it is we are going to talk about a few things about the dynamics of this flow. So firstly, let me mention that on this space x was the pair of point, direction, etc. There is a canonical measure. And how does it arise? At each point, you have the directions which have their own measure, and on the quotient, on this S that we have, which is at the base, there is also a measure which is from the upper half plane, right? Yeah. So our space X consists of pairs of points of this F together with directions. Now, along directions, of course, you have the measure theta, and along the this surface, you have the measure. Of course, you have also the measure corresponding to you could take dx dy, but that's not what we are doing. We are doing the measure corresponding to the upper half plane, the Poincare metric, and that is given by So the net measure is the measure corresponding to y raised to minus 2 dx dy d theta. So at each point, I suppose this should be clear. So in other words, if you have a function on x, you can integrate it with respect to this, and that will give you the integral. If you have a subset, you have to integrate its characteristic function to get what the measure is. So yeah, here this y here corresponds to the representation of p as x plus iy. The total measure of this is actually finite. That's something very crucial difference with. So the measure we obtain, the angular measure at each point, of course, is something finite. It goes only up to 2 pi, and the measure of this in the Euclidean plane, this has infinite measure. It's a long cylinder going up to infinity. But in the upper half plane, this is actually something of finite measure, because if you look at this integral y raised to minus 2 dx dy, this is x is running only from minus half to half, so that doesn't contribute anything, and y raised 1 over y square dy is something finite. So the total measure of the space x that you can visualize is finite. Now we shall modify. I mean, you can actually compute that value, but will not bother. I'll take mu to be a scaled version for which the total measure is 1. So we have a space together with a certain measure, which I have normalized to have total measure 1. And on that, I have the flow, measure preserving flow, pi t, which we defined. This is the geodesic flow, which moves along the geodesic. Now, this flow, interestingly, is ergodic. Now,
hello, sir. Hello.
Yeah.
Sir, can you show the description of x once before we proceed? I mean, I wanted to.
Can you show what?
The description of x, the set x.
Description of x.
Yeah. What was the definition?
X is the pairs points P from S.
So this theta is unit tangent with respect to my Poincare metric, right?
What is the question? At each point, you are taking the unit tangent, which you can take in the usual sense. They are conformal, so that aspect doesn't change.
Okay.
Well, you are right. If you are going only by Riemann geometry,
theta is the element of the tangent space at P, right?
You should think of it in terms of the Riemann metric as the unit tangent bundle of the Riemann metric.
Yeah, that's what I am asking.
But the interrelation is conformal. So though the lengths are not preserved, the angles are preserved. The transformation that we have, they have the property that though the lengths are not preserved, the angles are preserved. So there is no loss of generality in thinking of the angles just in the usual way. At each point, you can simply think of the angle in the usual way. It doesn't matter. We don't have to go to Riemann geometry for that.
Okay, sir.
Yeah. So now that is a space X, and on that we have the flow phi t, and we have the measure X, and first of all, the not said here. I think the measure is invariant under the under the flow. You know what it means? If I take a set and move it under, say, a particular phi t, then the resulting set has the same measure. So that's simply a matter of doing some calculation of integrals, etc., which I'll skip. and you can believe me that this has this interesting property that the measure is invariant under each of these transformations phi t, namely, which means that it is invariant under the flow. Now, another interesting property that it has is that it is ergodic. Now, ergodic being a flow being ergodic, a flow on a space with a finite measure which it leaves invariant, means that there is if you take any subset, a measurable subset, if it happens to be invariant under the set, invariant under the flow that you have, then the measure is either 0 or 1. What is it? So what is it saying? It's saying that you cannot split the whole space X into two parts, X1 and X2, both of which are invariant under the action of phi t, and both have positive measure. This is not possible. Let's understand once again what it. So I have a flow here on phi t on this space X. I have a certain measure mu which is invariant under the flow. Now, when you say that this is ergodic, that you say that it is ergodic when the space X cannot be subdivided, partitioned into two sets, both of which are invariant, and both of them are of positive measure. This is not possible. So one of them must have 0 measure. If you partition into two invariant sets, one of them must have 0 measure, other must have measure 1. That's the only possible scenario that happens. The proof of this involves a bit of work, which it may not be canonical, but then I don't think we'll go into that. Okay, so. Now, why do we have notice that if I can only say that you cannot partition into two of both of positive invariant sets which are both of positive measure. Of course, it is possible to have non-empty sets which are of measure. So if you take a single orbit, for instance, okay, so it's a single curve, and its measure, you can imagine, is going to be 0. So you can take such a single trajectory of the flow, which is then invariant, and look at its complement. That is both the orbit and its complement. They are invariant sets, and together they cover X. This doesn't contradict ergodicity, because all we are saying for asking for being ergodic, or the property of ergodicity, is that whenever I choose such a partition, it can only happen if the set, one of the sets is of measure 0 and the other set is of measure 1, and which is in fact and this is true in this case. And this again, this is going to be a further digression, but I think it may be worth mentioning here that it is also mixing. It's also a mixing flow, and what that means, if I take the two subsets, A and measurable subsets A and B, and apply phi t to one of them. So you have these two sets. You apply, you move one of these, and keep looking at the intersection for various t. Okay, so and looking at the measure of this. Mixing, what it tells you is that as t goes, so if you wait for sufficiently long time, the measure of this intersection is actually equal to the product of the measures of these two, so that they cannot. First, in particular, for instance, assuming these are positive measure, the intersection will always remain will have positive measure, and it will sort of it'll bounded away from zero. So they'll keep for all large t. These will be intersecting, and the intersections will have a certain precise proportion, etc. This is kind of useful property. So anyway, so this will not concern us more, but let me just recall only the ergodicity, emphasize only on the ergodicity part. Now, one consequence of ergodicity is that almost all points, almost all orbits. Orbit is something which, I mean, when you have traced for any point, given a flow, if you take all the points that you get by following the trajectory phi t, and all the points t positive, and all the points that you would get by following the trajectory in the negative direction, that is the orbit. And one consequence of ergodicity is that all the orbits are dense in X. I suppose you know what dense means. They go arbitrarily close to all the points of X. Why is that? Because if you look at take any open set, take a neighborhood and look at all the points that will go close to that sometime in the future or sometime in the past they have been close. That is an invariant set. So if you saturate an open set, then it's always a set of full measure. And from this, it's a simple exercise to see that the set of points for which the axis, this is dense. This is actually a set. The complement of this set has measure 0. So there is a certain set such that for every x in this subset, the trajectory, the both sides trajectory, the orbit is dense, and the complement of that is measure 0. So almost typically or generically, as they say, if you pick a trajectory, it is going to be dense. There is no natural concrete description of this. That we will talk about. What will be it turns out that though this subset is large, it is the complement that interests us. So this situation is somewhat like this: in the real numbers, the rational numbers they're countable. They form a small set, right? But it's the rational numbers or the algebraic numbers that those interest us in a certain way more than a generic typical irrational number, something that is special. So the considerable amount of interest lies in the points for which this is not dense. So on the one hand, we know that almost every point the orbit is dense, but we would like to understand things which are not dense. So something we would like to focus on when this generic behavior does not happen. We want to look for special kind of behavior, and that's what we want to analyze in terms of numbers, etc. So here are some types. So periodic orbits. There are orbits in this which are periodic, and so this will have. And this happen in the following way. If you take an element of SL2Z, so which has two eigenvalues, which has an eigenvalue lambda greater than 1. So for instance, you can take 2, 1, 1, 1, etc. And the other eigenvalue will be lambda inverse, right? So now this lambda and lambda inverse. Let me go to the picture diagram. Yeah. So the geodesic in the hyperbolic plane is a semicircle, and what you are seeing here is the image of that under the quotient. Now, if I take a geodesic, which say I explained that element gamma. So if you take the semicircle which joins lambda inverse to lambda. Okay, then these are eigenvalues of the gamma, and it will turn out that this geodesic will be periodic, because what happens is when you follow this according to time t, then at some time you will hit gamma, and then in finite time, and then that point will be same as the original point. So this way you get periodic geodesics, and if you have a direction, if you have a point in that and a direction which goes along that, then that will be actually a periodic trajectory of the geodesic flow. There are another type, if it is periodic, then of course it is not going to be dense, because its closed periodic part is a certain compact set, and you will not reach anything outside that. So similarly, divergent orbits correspond to, so if let's look at the vertical lines here. For instance, if I take a vertical line, then this forward segment that I have is a closed subset, right? This is a closed subset of the surface, and so in particular it is not dense. Now here I took only a forward part, but if I go back, and if this endpoint happens to be rational, then that means if the endpoint is rational, then the representatives of the inverse, they're also going to be like going upward. So that will mean that if I have a vertical line with a rational x coordinate, that is a geodesic which is closed. It's a geodesic associated with the modular surface, which is actually closed. So that is not dense. So such a thing is called a divergent orbit. So these are two main important classes of points which are for which the orbits are not dense, but there can be more somewhat more complicated situations. So it would be as you saw when we analyzed two parts. So given the whole orbit, it's always enough to look at the two parts independently, going forward and going backward. You can analyze separately and then ask their topological properties and put them together. So. In particular, the orbit will be dense if and only if at least one of the forward or backward trajectories is dense. This is a little bit of proof, but we'll not go into that. So now, let's therefore think only of just the forward trajectories in this case. So now. And with each trajectory, so we are looking at therefore we are looking at parts of semicircles with only a forward. We are going in one direction. So there is an end point. Each forward geodesic is an associated end point. And similarly, if I take the orbit of a flow, of the geodesic flow, then it is lying over a geodesic, and then correspondingly it has this endpoint. Now it is this endpoint which is the thing that we are going to focus on. And here is one more property that is of interest. Let gamma t be a forward segment of a geodesic, and alpha be its limit point on the boundary. That is the end point that I described to you. Now, one can show which is this is elementary, but again we don't have the time here. That considering all possible representatives, it can be seen that if there exists delta such that alpha minus p by q is greater than delta by q squared for all rational numbers, then the representatives of this gamma t in F have their y coordinates bounded. So if so alpha is the end point, and at that end point, if so rather than going to this picture, let's just imagine the real line here, and I have this alpha. Then look at the rational points along that. Now, if for each rational point p by q, the distance from alpha is greater than delta by q squared for some fixed delta, and as q runs over all integers, then if you transform this picture and look at the representatives in F, they will be bounded. It will not. The imaginary parts will be bounded, and therefore they'll lie in a compact set. So such a trajectory is called a bounded trajectory. So and once it is bounded, again it cannot be dense. So we have a variety of special trajectories which are not dense. Now I just mentioned that if this happens, then do we know that there are such numbers for which it is true? And yes, this is true. This is a very standard collection of numbers in number theory called badly approximable numbers. I'll say a little more about this as we go further. So though the collection of points on the geodesic, for which the geodesic flow is dense, it's a full measure. There are whole variety of points which fail to have dense orbits, and in fact they are of interest to us. And particularly, while the earlier the periodic trajectories, they are only countably many. Similarly, the divergent ones, there are only certain countably many. Of course, countably many lines. However, it turns out that these objects, they actually form a very large set. So though their measure still has to be 0, but there are other ways of gauging the size of a set, and something called the Hausdorff dimension, and it turns out that it has the maximum possible Hausdorff dimension for the subset of real numbers as far as the endpoints are concerned, and hence subset of these of X, which is three-dimensional. Now, a bit about say a few things about the relation of this with continued fraction expansions, which is rather the interest, which sort of connects to the arithmetic and some of my own work, etc. So let me quickly recall what continued fraction expansions is. Hopefully some of you may have familiarity with it already. So starting with any number, this is now over real numbers. Starting with any real number t, I can write this as a0 plus a remainder r0, which is strictly between 0 and 1. It can be 0, but not 1. Now look at this r0. If it is bigger than 0, then I'll take t1 equal to r0 inverse. It is greater than 1, and then I can write t1 as a1 plus r1 with r1 between 0, possibly equal, but strictly less than 1, and so on. And you can convince yourself that eventually repeating the procedure, we see that either t can be written as a0 plus 1 over a1 plus 1 over a2, etc., going on up to 1 over ak for some fixed k, or there is an expression of this form, a naught plus 1 over a1 plus 1 over a2, etc., going up to infinity. Now, one might wonder, does it make sense to talk dot, 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 dot? We have, of course, studied series, which means, you know, that it means something specific to write dot, dot, dot. But when you say this, what does dot, dot, dot mean? But it does, what we mean is actually that if you, first of all, you know how to construct. If this does not hold for any k, then you know how to construct this sequence a0, a1, a2, etc., aj or j going all the way to infinity. So for each finite, up to some finite step, you look at only that fraction. Now you have a sequence of rational numbers. Okay, and what it means to say that t equals this with the dot 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 is that this sequence of rational numbers that you get, if you ignore the part after some stage, okay, this each of these, of course, is a rational number. So this sequence of rational numbers converges, and not only it converges, it actually converges to t. And that is the sense of writing t equal to this. And of course you need some justification, but the justification exists and it's not very difficult if you think about it yourself. So each real number can be understood by such an expression, either of this type or of this type. And what I've introduced here is called the simple continued fraction expansion of t. Now, simple continued fraction expansion, as the name suggests, is a special case, and there are also other continued fraction expansions. And another one which has been of interest to me, particularly, I've dealt with a whole variety of continued fraction expansions, but a special one which I'd like to introduce here is something which you do something similar, but instead of asking for the remainder to be between 0 and 1, you ask for it to be between minus half and half, and you see that also has to be possible, right? And you do the same thing as before, and therefore you can write t as equal to a0 plus 1 over a1 plus 1 over up to ak for some k, where what you now have. Now notice that because I was allowing negative numbers here, these can be negative integers, right? And the only thing, so continuing thing is when the remainder is not 0 at some stage, I'll have to go on indefinitely, and in that case I'll get an expression like this, where a0, a1, a0 of course can be any integer in either of the expansions. Here in the previous one, all the later ones were non-negative, were bigger than or equal to 1. On the other hand, here all you say is that they are non-negative, non-zero integers. Not only that, their absolute value is actually bigger than or equal to 2, because the remainder was always bigger than or equal to, remainder was less than or equal to half, the way you chose. When you invert it, it is bigger than or equal to half, so in absolute value. And the absolute value of the successive ones is equal to be at least 2. And there is a further condition that it satisfies, but we will ignore that for the present. So there are two such expansions which are really interesting. Okay, so now the relations of this with a geometry of the modular surface. A geodesic in S is periodic if and only if the continued fraction expansions of the forward and backward trajectories are eventually periodic. So what now we are talking about the interrelation between the rather than going back to the diagram seems a bit complicated. So we have what are we talking about? We have these geodesic segments which are forward parts of a semicircle. Of course, it can be directed this way. It's a semicircle, one segment of a semicircle, and it has an endpoint. Now we are relating the arithmetic behavior of this endpoint to the geometric behavior of the geodesic, and correspondingly the dynamical behavior of the associated geodesic orbit. So the first comment here is that the this. When is this? We saw that there are periodic geodesics. Now it can be characterized in terms of the endpoints, and the condition is precisely that the continued fraction expansions of these are eventually periodic, which means that after some stage they keep repeating themselves. A of j plus p is equal to a of aj for some j bigger than or equal to k. A geodesic trajectory is divergent if and only if the endpoint is rational, which holds if and only if the continued fraction expansion of the endpoint is finite. So again, it's completely determined by the continued fraction expansion of the endpoint. Now here I didn't tell. I'm just using continued fraction expansion without telling you which one, but it applies to both the ones that I introduced to you. A more deeper theme which has been pursued considerably in literature quite considerably is that a geodesic trajectory is bounded if and only if the continued fraction expansion aj corresponding to the endpoint is a bounded infinite sequence. So infinite sequence means first of all, if it is rational, then we know that the trajectory is divergent, then it is not bounded. And so the sequence being bounded, AJs being bounded. Recall that these AJs in either of the cases where integers, either integers or integers bigger than or equal to 2, etc. So they have typically, if you try to look at such a sequence, then it could be unbounded. And the property of the geodesic being bounded, the geodesic trajectory being bounded, corresponds exactly to the these AJs in the continued fraction expansion being bounded. Apart from this, there are also, so these are some of the very at the beginning of the theory. Now there are various extensions, ramifications, etc., which I'll tell you briefly. So yeah. Here I have said that the bound on the AJs is precisely related to the bound of the geodesic in some precise ways that which are not brought in here. Okay, so now what are some of the later directions? So there are various directions in which the theory extends, and which we shall not go into here except to indicate a few of them. So in my work with Manoj Chaudhary, the interaction with the Hurwitz continued fraction expansion is used to produce geodesics with reaching given. So if you think of reaching a height, with what frequency do you want it to go there? So the control you can obtain with a certain control on the continued fraction expansion that you choose. You can have the desired control on how frequently the geodesic trajectory will visit a part above a certain height in that set F. So the quantitative relation between these two, and the reason why we're interested in this particular aspect is that the geodesic flow is also related to the values of quadratic forms. Now there's been a lot of study of values. If a quadratic form is an expression of the form summation sigma xi xj, which is symmetric, in sigma aij xi xj, which is symmetric, and the values of quadratic forms have played a very important role in some of the mathematics of the last half a century or so, and there are some important conjectures about quadratic forms which are solved in the 1980s by Margulis. And so, but all of that actually corresponds to the much of the known theory and well understood theory concerns the quadratic forms in 3 or more variables. The quadratic forms in 2 variables, which is what we are looking at here, are kind of different species in some way, and their study is carried out through the study of the geodesic flow, and some of our results make a comparison to what happens for quadratic on the questions that are involved in study of quadratic forms, how they compare 2 variable situation with the higher variable situation, etc. Will not go into the detail. Now, I sort of introduced the general picture of some almost all orbits being dense, but emphasize that I'm going to the complement. I mean, I gave the example of being interested more in rationals, though they are only of a small. They are a small subset in some sense. But on the other hand, there is a considerable amount of theory which relates the generic picture also. The properties more intricate interrelation is established between the geodesic flow and continued fraction expansion in a comprehensive form, in a form of coding of geodesics. So, though here I introduced interrelation between continued fraction expansion with non-dense orbit, there is a similar interrelation between the dense orbits and properties of continued fraction expansion, which we will not go into. So there is the work of Karlin series, Svetlana Kotov, and others, and some of the early observations in that go back to a paper of Hartin, where he obtained some of the properties. I mean, existence of dense orbit, etc., without the benefit of knowing ergodicity and so on. And let me also say the theory is extended to higher dimensions. We are all in all the things that we talked about, the surfaces and the boundary, which is the real line. Much of this theory extends to higher lines, but not that once the boundary is not just the real numbers, you no longer have a good theory of continued fraction expansions. So it has to be in terms of other structures and so on. So, however, there is such a theory which in some sense is, in a good sense, is a continuation of this, but there will be no time to introduce that. So I've already overshot considerably. So with that, thank you all for your attention.
Okay, so thank you, Professor Dani, for this wonderful survey. I shall appreciate if you send me the slides. Those are nice survey.
Sorry?
If you can send us the slides, that would be nice.
Send the slides.
Slide, yeah, certainly. I'll be happy to send this presentation.
Yeah. So is there any question from the participants? Any questions? Professor Kulkarni, yeah, you can ask.
Can you write
Professor Kulkarni?
Can you write down some formula for the geodesic flow in terms of x, y, theta goes to x prime, y prime, theta prime, as
Can you
functions
write
of
down the formula for flow?
Can formula in terms of what?
some x, y, theta. These are the coordinates on your
No. No, you can write it. I mean, as an integral, you can write, but the integral doesn't have any closed form. No.
No, sir.
I don't know if this answers your question, but
X, y, theta goes to x sub t, y sub t, theta sub t.
X, Y, theta, theta, going to what? Formula for the flow.
So
no, I'm not aware of any closed form expression. You have to write it as an integral.
okay, what is the integral form of that?
No, because phi t is defined by as the integral, right? So you write the corresponding integral.
Yeah, okay, all right.
No, there is no simple expression. I'm not aware of any. No.
Okay, so is there any more questions? Any more questions? So Professor Dani, I have a question. So if you replace modular group by some other discrete subgroup of SL2R, so can you say something about them?
Firstly, you would need you would need that the quotient is non-compact, and with that there is some kind of sense one can make for the corresponding boundary and continued fraction expansion, but I don't think there is any rich or developed theory about it.
Okay. So suppose you take the ring of Gaussian integers in SL2C.
Pardon?
You take the ring of Gaussian integers in SL2C.
Yeah. So then some of these things extend, but not every.
I see.
Then you do have continued fraction expansion. That there actually it is the Hurwitz expansion.
Okay. Okay. Okay.
Yeah.
Okay. So is there any more questions?
So some reference for these modular groups and these things, the first part.
References.
Some reference. There's I don't know exact reference, but I mean you can try it. There's a book of Becca and Mayer, ergodic properties. So that book has some introductory things which.
So there is a book by Dalbo called Geodesic Trajectories and I think Hyperbolic Surfaces. Dalbo, just a small book.
Okay.
Yeah, that's a nice book. Yeah. So it's an undergraduate text in mathematics book. So that's a nice book, I think.
Okay.
What was
okay, so if
what is
Dani has another question.
No, what is no, I just want to know what was your reference, the book.
Becca and Mayer, the book by Becca and Mayer.
The book by Becca and Mayer, yeah.
Yeah. So the book I was referring called Geodesic and Horocyclic Trajectories.
Okay, yeah.
François Dalbo. Yeah.
François Dalbo, yeah.
Yeah. Okay.
Yeah.
Okay. So if there is no more question, then I would like to thank Professor Dani. Yeah, Professor Kulkarni is asking something. So any more question? Any more questions?
No, sir. Thanks from me.
Okay. So thank you, Professor Dani, for this wonderful talk. and we really appreciate that you find out this time from your busy schedule. So thank you very much. Thank you very much.
My pleasure.
Okay, so Gauri Shankar, shall we close the session?
Yes, sir. Yes. Yes.
Okay, so we meet at 2 o'clock.
Yes. Yes. For next session.
Yeah. Okay. Okay. Thank you.
Thank you.
Thank you. Bye.
Thank you.
Bye.